Day 2. Yesterday we learned how temperature drops as you climb. Today we build directly on that with Formula 2. How pressure changes with altitude. This one matters even more directly to pilots because your altimeter is literally a pressure sensor. It doesn't measure height. It measures air pressure and then converts that into an altitude reading using this exact formula. So it also feeds tomorrow's formula, density. So if you are following the series, today's equation is the bridge between day 1 and day 3. P equals, so P0 times the quantity 1 minus LH over T0, all raised to the power G over RL. It looks intimidating compared to yesterday. So, but every symbol is something we already know or can look up. P is the pressure we are solving for in pascals. So P0 is sea level pressure. The ISA standard value is 101,325 pascals, which is just standard atmospheric pressure. L and T0 are the exact same constants from yesterday. So lapse rate is a 0.065 Kelvin per meter. Okay, and sea level temperature 288.15 Kelvin, and H is altitude in meters, same as before. The two new symbols are in the exponent 9.81 meters per second square, and R is the specific gas constant for air 287 joules per kilogram Kelvin. Both are fixed physical constants. You don't calculate them, you just know them. See, here is a trick that makes this formula manageable. The RL never changes because G, R, and L are all fixed constants. So calculate it once. 9.81 divided by 287 times 0.065. So, and you get a 5.2586. So write that number down. You will use it in every single problem. So really, P equals P0 times the quantity 1 minus LH over T0 raised to the power 5.2586. That's it. One constant exponent every time. Now the intuition as the altitude H increases, LH so over T0 increases. So now as the altitude H increases, the fraction LH over T0 increases. So 1 minus that fraction gets smaller. 1 minus that fraction gets smaller, and a smaller number raised to the power gets smaller. Still. So pressure keeps dropping as you climb. Uh, Pressure keeps dropping as you climb. But notice it's not a straight line like temperature was. It's a curve because of the exponent. The pressure actually drops off faster than temperature does. Same two altitudes as yesterday, so you can directly compare how temperature behaved. So first 3,000 meters, a light aircraft, then 10,000 meters, airline cruise. The worked example, so here find example from this worked example from find the air pressure at 3,000 meters. So the step one, write the formula, then P equals to P0 times 1 minus LH over T0 to the power 5.2586. Step 2, list our nodes, okay? List our nodes. 101,325 pascals. L is 0.065. H is 300 meters. T0 is 288.15. Work out the inner bracket first. LH is 0.065 times 3000, which is 19.5. So divide that by T0, 208.15. That gives 0.067. Right. Step 4, subtract from 1 minus 0.067 equals 0.9323. So step 5, raise that the power 5.2586 on your calculator. So that's 0.9323 to the power 5.2586, which equals approximately 0.6917. Step 6. Multiply by P0. 101,325 times 0.6917 equals approximately 70,095 pascals, or about 70.1 kilopascals. So that roughly 69% of sea level pressure. So example 2, 5,000 meters, typical airline cruise. So same 6 steps. Inner bracket first, LH is 0.065 times 10,000, which is 65, divided by 288.15, giving 0.256. So 1 minus 0.256 equals 0.74. So rise at 0.74 to the power 5.2586. That gives approximately 0.2607. So multiply by P0, 101,325 times 0.2607 equals approximately 26,418 pascals, about 26.4 kilopascals, so roughly 1/4 of sea level pressure. So think about it. At cruise altitude, the air pressure outside the aircraft is only about a quarter of what it is at sea level. So that's exactly why the cabin has to be pressurized for passengers to breathe comfortably. See now, three quick mistakes to avoid. First, always compute the inner bracket completely before applying the exponent. Don't try to combine steps in your head. So second, the exponent of 5.2586 is fixed for this formula only because it depends on G or and the standard L. So if your question changes L, you must recalculate the exponent. Don't assume it's always a 5.2586. So third, sanity. Check your answers. Answer: pressure should always be a positive number, smaller than 101,320. If you get so third, here the sanity check. Your answer: pressure should always be a positive number, smaller than 1,325 pascals. So within this altitude range, if you get a number larger than sea level pressure, you have made a sign or exponent error. Go back and check. Okay. So now recap. So let's recap. P equals B0 times 1 minus LH over T0 to the power G over RL, which works out to 5.2586. So P0 is 101,000 pascals, valid from sea level to 11,000 meters. So your practice question for today: find the pressure at 5,500-meter altitude. Use the same 6 steps we just used and drop your answer in the comments. I will pin the correct one. That's formula 2. Down. Tomorrow, day 3, we complete standard atmosphere formula and how air density changes with altitude, which combines everything we have learned in days 1 and 2. See you then.